I read the first half and then like skimmed the other half because I didn't have time, and then looked at Spark Notes and like I knew what's gonna happen.
I read 1984. I read Animal House.
Animal Farm?
Yeah.
Yeah.
Animal Farm. How did see what happens? I've got too much in my brain.
Have you read Stranger in a Strange Land? I watched YouTube video and I was like, nope, that's.
I read Invisible Man.
Yeah.
What's that?
I want to read looking at new Android Stream of Electric Sheep. Got that one recommended to me a lot.
I heard about that one. I haven't
All
read
right.
it.
There's a book based off of it. It's
Make sure you check the keys. Compare your homework to the keys. Ooh, let me check the blackboard. Think about this. Yes. So I do. We will talk about the exam.
Will you hear anything else about the botany professor?
Yep. Well, we know when they're coming in. All right. So. Okay. So we do have. I did post some extra stuff. Yeah, it would have to be updated because we will have. We're gonna work through the confidence intervals, doing these confidence intervals in R. All right, and that's our test. So we have homework number 8, extra hypothesis testing confidence intervals. It's a PDF. It's not like uploading it. So it has just kind of general questions related to this, related to this part, this presentation. You could use this as a study guide for the new stuff. I mean, there's more that we covered, more definitions that we covered and everything. But, and we didn't, I mean, we'll get to rounding, but at least for this exam, we're not going to have the rounding. We are going to do like t distribution. So I'll ask you, what's the t value that you'll use for the confidence interval? And that's kind of like this, right? And then we'll do, and you can use the table. All right, you use the table. And then in R, we're going to be doing like the confidence interval. So I say that for number 7, it's like do it by hand. As long as you know how to do this in R, it'll be good. All right, it'll be good. So that's posted with the data set. You can do it. I think what we'll do is I have the key for this. So I'll post the key after class. Please try to do this on your own first, and then that way you can, if you're doing it correctly and it matches the key, hey, that's great. You should be good for the exam. All right. So our exam will be on Monday. The closed book part of the exam will be during our lecture time. So at 11 o'clock, the botany candidate that's coming in, Dr. Howard, has their, I think the teaching demonstration is at noon. Or at 12:15. It's at 12:15, and I don't know where. I accidentally printed out two copies of the schedule. So let me get it. Now I'll remind you all on Monday where it is. But at 12:15, so once we finish up, they'll do the teaching demonstration. Yep, it's in Cabinets 100 upstairs. And then at 3:15, the research presentation will begin. So that is during our exam, during the lab part. But since we're going to do the closed book part during lecture, the only thing you'll have in lab is the application part. So with the application part, it's going to start at 2 o'clock. What I'll do is I'll make it go live at like 1:45. All right, I'll make it go live at 1:45. So that way you can come in if you want to start early, you can. Should it take 2 hours? No, it shouldn't. All right, it shouldn't. If you're comfortable working in R, importing your data set, doing the libraries, checking normality, using the binomial function dbinom, dpoisson, or dpoise, R norm, P norm, using all that stuff, it should be fairly easy. All right, and it's not, I know like the homework has, might have 4 or 5. We had like 4 or 5 of the P norms, like right in a row. I don't really have to have 4 or 5 to demonstrate that you know how to do it, right? Or how to use the function. Like you're not going to have 3 or 4 QQ plots to make. To demonstrate you know how to make one and can interpret it, that's going to be sufficient. And then you'll also be making a lot of QQ plots later on. So that's our plan. The research presentation is also up in CAV 100. All right.
Do we know like what the research presentation is on, or is it a surprise?
It's not labeled.
Okay.
But I can show you.
I was just curious.
Who he is.
The last one was it was like labeled with what. Here's what the research topic was on.
Yeah. Here, let me. He does have a web page. Right here. Check him out. I should have probably like stopped the live stream. Check it out. Yeah, it's Dr. Howard. So if you do like Cody Howard Botany, you'll find it. His research does geophytes and bulbs and stuff, like below ground growth and evolution. So it's still plants. It's stuff that he could probably do here. I don't know. It sounds interesting. Curious to hear what he has to say about it. He's done field work several places around the globe, so seems like interesting talk. So that's why we'll have time where you can go up and do the teaching demo, and then the research demo is 3:15, and hopefully everyone's done with their exam at that point. All right. And then again, I hope to get the exams back by that Friday.
Is this chapter on the test, or will this be the next test?
Just up through the confidence intervals of the mean. So yeah, what we're gonna be doing is like I have stuff where like we do it by hand, but we're not gonna be doing this by hand. We're gonna be using R to do it, and then we're gonna stop basically right here because the reporting error is part of significant rounding. So we'll have reporting error, and then we'll talk about some of the graphics on how to report some stuff. So yeah, we're just stopping at the confidence intervals. So that's where we're at. And that's why that homework number 8, it's marked as extra. Homework number 8 extra. Again, I'm not going to collect it, so this will be a free one, but make sure you try to do it, because if you can't do it, you'll probably miss the question or 2 or 3 on the exam. Bring a calculator for the closed book, because we did do some of the P norms and stuff by hand. All right. So, review. Calculation of these confidence intervals. The mean plus or minus or t critical value. times our standard error, where the standard error is our sample standard deviation divided by the square root of our sample size. Why do we do that? It's because we are trying to approximate the population level standard deviation. All right, so we do that with our S. All right, so here's the example. We measure 20 raccoon canines. They have an average length of 23, variance of 2.5. So we want to calculate the 95% confidence interval of the mean. If we were going to calculate it by hand, all right, I have this, we would do something like this. We go to the formula, we've got our mean, we've got plus or minus our t-critical value, all right, and the standard error. So we would have to, the mean is already given to us, that's 23. We would have to go to our t-table, let me open that up, go to our t-table to get our t-critical value. So, that's not it. Which one did I put? I think I posted this one. Rotate it. There we go. So I believe we put this one up. So we did 20 raccoon canines. Our sample size is 20. All right. We want a 95% confidence interval. So 95% confidence interval means we have 5% in the tails, 2.5 in each tail. All right, so I'm going to read down my 5% column. I'm going to go to the degrees of freedom, not our sample size. So our sample size is 20. What's our degree of freedom? 19. So it's one less. So our degrees of freedom under the 5% is 2.093. That's our critical value, and that's what I have at here. And then what we have to do is calculate the standard error. Now the standard error is the standard deviation over the square root of our sample size. All right. The standard error is S over square root of n. This is also the same as this. Right? So if we have a variance, the square root of the variance is the standard deviation. And just from math, we can do that. So if you have variance, it's just variance over the sample size, and then take the square root of that value. Right? It's the same things. So that's what I did here, and that's why I kind of did the simplification. The reason why I did that. But then I get, so this 2.093 times the standard error gives us 0.74. So our confidence interval, 95% confidence interval, is 23 plus or minus 0.74. Or we can express it as a range, so take 23 minus 0.74 and 23 plus 0.74 to get 22.26 up to 23.74. How do we do it in R? Well, in R, we use the exact same formula, but now we're going to let R calculate the t-critical for us. All right, so we left off with our R markdown document with calculating the QT, or using QT to calculate our critical values. And we said that if we give it the lower and upper value, R will return the plus and the minus, and those values should be the same if we're doing one of these confidence intervals. So what we can do, we measured 20 raccoon, let's see here, 2 C's, canines. Let's get this. Our mean was, I don't know what it was, 23 and 2.5. Mean was 23, variance is 2.5. Calculate the 95% confidence interval. All right, that's our task. That's the example. Let's move this down. All right, so our equation again is the mean, plus or minus, actually, plus our QT function, right, times the standard error. All right. Now, our STERR function works with a vector. When we have data like this, we actually have to manually calculate the standard error. So I'm going to just type this in. So we've got 23, that's our mean, plus our t-value. That's going to be our QT. We're looking for a 95% confidence interval, so that is 0.025 and 0.975. So we're looking at 2.5% to the left, 2.5% to the right, and it gives us this upper and lower bound for our percentiles. Our degrees of freedom is 19, so 20 minus 1. Then we're going to multiply by our standard error. And we have to calculate this by hand. So our standard error is the square root of our variance, 2.5, divided by our sample size, 20. Now remember, QT gives us a plus value and a minus value. And since we use the plus here, and since we have the vector of two values, this function will first utilize the negative value, and then it'll calculate it for the positive value, so it returns two values here. 2.26 up to 23.74. All right. So we will try this. Zoom in on this. All right, so these will be next two practice problems. All right, example 2. So these will be practice from homework number 8. Oops. All right. We're going to calculate 95% confidence interval for this sample. All right, so the mean is 13.3. Standard deviation is 1.25. And our sample size is 12. All right, and this is, you're going to see that these data, this is number 8. This is the calculate by hand the specified confidence intervals for these data. So we'll do these two as practice here in class. All right, so go do that. I'll type this out. You're working on it. All right, did you get this first one? So we're just doing it the same way. So our mean is 13.3. We're going to add our QT value. So it's 0.025 and 0.975. That gives us our 5% in the tails. Our degrees of freedom is 11, and we're going to multiply it by our standard error, which is 1.25 divided by the square root of our sample size. So if it makes it a little bit easier, we can always use our parentheses to kind of specify our standard error is this value, 1.25 over the square root of 12. And when I run that, I get these confidence intervals. And I rounded here. So the second question then is also 95% confidence interval. Got a mean of 18.9. Variance is 2.67 and a sample size of 18. So calculate the confidence interval. Yep. Oh, because you did square root of 1.25 over 12. That 1.25 is S. 1.25 is standard deviation. That's S. So if it's standard deviation, if you get standard deviation, you do that. If you get a variance, you can do that. Yeah, so your standard error is a little different. Here's my range. So doing these by hand, terrible. R makes it a whole lot easier. R makes it a whole lot easier. Using vectors isn't as bad either. So what we're going to do is generate a random vector just to demonstrate how we would do this. And then instead of using a homework assignment, what we'll do is we'll open up one of our, probably the QQ, or the continuous variable one, the one that we use to check normality. We'll open that up and pull a couple of those vectors out so that we could demonstrate confidence intervals with a vector. So I'm going to ask that you run this Rx command. So this Rx function is going to, well, we'll talk about what it does. So So what did this do? What was this function? This Rx. If I say, tell me what this function did, what did it do?
It generated a list of numbers.
Okay.
Main
What's that? Yep, generate random sample. How many? 50. All right, what is the mean and standard deviation of our sample? Well, yeah, it should be 50 and 2. We're drawing a random sample from this distribution. Doesn't mean we'll actually get it. All right, we'll have some variation. Maybe it's 50.1, maybe it's 49.9. Who knows? But we're drawing this random sample, so we have a vector. That's what we have. All right, so I ran it, so we have that. I do have to go up and run my standard error function because we're going to need it. So let me find it. There it is. There's my sterr function. All right, so I ran it. I have it accessible. It's in my environment now. It's there. All right, so we have our vector. So our confidence, what is the 95% confidence interval of the Rx vector? All right, again, it's mean plus our Qt function times our standard error. All right. In this case, I'll use sterr. So we're going to do the mean of the Rx vector. All right. If it helps, we could use na.rm equals t. All right, but we didn't add missing data. And then we're going to use our Qt function again to get our t critical values. So since we're asking for a 95% confidence interval, it's the same 0.025 and 0.975. Our degrees of freedom, though, how do we get that? Yep, and -1. I'm going to use length of the Rx -1. So since I know we have no missing data points, I'm just going to pass the length of Rx -1. If we didn't want to use this, how do we find out how many data points we have? Yeah, we can look at the environment. So this shows us it is 50. Let's move that.
So, I have nothing showing up in my environment. I've run it a couple of times and it's still not working.
Yes. Save your script, save your RMD file, close out our studio, and then reopen it. That worked for me last week. Yeah, not sure why that happens. Not sure why that happens. So yeah, we could look at that. We could also do a summary. So if I did summary, come on, summary of Rx. No, it actually doesn't give me that. Doesn't really give me that. Okay, I lied. But I like the length. I just like passing it there. So that's our Qt function times our standard error. Since we have a vector, a numeric vector, let's use our standard error function. So sterr times the Rx, which is our vector. And when I run it, it gives us our values. So we have 49.86 to 50.88. What's that? Is that what you get? Yeah, your numbers are different. Why are they different?
We didn't set a seed.
Yeah, we didn't set a seed. So, yeah, that's why, you know, yeah, we ran it. Our numbers are going to be different than this. So, let's do, I'm going to import data set, one that we've used. Let's go to our data. We did we have normality practice, right? Yeah, we do. Normality practice. So I'm going to import that. Notice again, you remember our issue is that for some reason it didn't have heading checked. So if you do no, then you'll get these V's at the top. So I just want to make sure I have the heading as yes. All right. And we can do strings as factor. But I'm going to import that. Normality practice. We used that last week. And some this week on Monday, I think. We got normality practice here. I am just going to go ahead and copy and paste this. So practice problems. So we'll use normality practice.csv. Right. So I'm going to make sure I have header equals T on here, since it didn't really add that. I mean, I think header equals T is the default, but I'm just going to make sure it's there. So if I rerun this, I don't have any problem. And then what I'm going to do is do Q1. I'm going to pull out Q1 and also Q2. And I can't remember if we have missing data or not. So when I pull them out and save them as a Q1 vector and as a Q2 vector, what function will remove all of our NAs? NA.rn will remove it in like our mean and standard deviation functions. I'm going to use NA.omit. So I'm going to take the vector, omit all the missing data points, and then save it as a new vector. So that way I don't have to type this normality practice Q1 over and over and over again, and we don't have any missing data. All right. So we're going to use just these two vectors. All right, I'm going to make sure I run the chunk. So I have Q1 and Q2. All right. So we're going to calculate, let's do the 95% confidence interval for Q1. So we'll do that one first. All right. And then for Q2, how about we calculate 99% confidence interval? All right. Oops, yeah, I'm going to move that down. So go ahead and, since these are vectors, go ahead and calculate the 95% and the 99% confidence interval. And now we should all get the same answer, since we're using the same vectors. Here's my value. Again, we imported the data. We pulled out that Q1 vector and stripped out all the NAs, which I don't think there were any NAs in the Q1 vector. But once we have that vector, Q1s, our confidence interval is mean of that vector times the QT value, which gives us a 95% confidence interval. So the 0.025 and 0.975 degrees of freedom is that the length minus 1, and then times the standard error, STERR, times Q1. And I get 2.92 up to 3.05. What you get for the 95% confidence interval? All right, what you get for the second one? Is it 3.75 to? Everyone get that?
No.
What'd you get?
3.68 to 4.3.
3.682. 4 point what? So here we changed our confidence interval. We went from 99 or from a 95 up to a 99. So what percentage is in our tails? 1%. What percentage is in each tail? 0.5%. So here we're going to go 0.005 up to 0.995. So that gives us 5% or 0.5% in each tail. So when we get this, we get that. As I said, for the most part, we're doing 95% confidence intervals. But if you needed to do a 90% or a 99%, we can do it. So,
Zoe can't seem to do zeros.
what's that?
Except for Zoe, can't seem to do zeros. Again.
All right, so let's talk about interpretation. So in that first example, we had 20 raccoons, right? We did our confidence interval. That's interpretive. What does that mean? You go up to a raccoon. Here it is. What does that mean? If I say interpret this interval, how would you interpret it?
The majority of the measurements were between 22.26 and 23.74.
The majority of these measurements?
95%.
No, probably not. So I'm going to go to this RS vector, and we're going to check that. The RX vector we have, that was our confidence interval. So we had 50 values. So what I am going to do is I'm going to count the sum of the RX values that is below the 49.86. And I'm going to divide that by 50. So this will, you're going to see this again, but what I'm doing is trying to count up how many values are actually below the lower end. 34% below the lower end. 34% of our actual values are below that. So it's not, confidence interval is that 95% of our values lie in this range. Where are we? Here we are. It's we're 95% confident that this range captures the true mean of canine length.
Oh yeah, I can't be involved with it. It has to be captured.
Yeah, we have to capture it. It's not that the true mean falls in this range 95% of the time because the true mean is a fixed value. It's not going to move. And you can wonder, well, why isn't 95% of our values in this range? And it's because our values take on a wide range. We use the collection of values, that sample, to estimate our mean. That's what we're trying to predict. And that's why some of our samples, perhaps a lot of our samples, will actually fall outside of that range. For every value in our sample that's below our range, we're going to probably have a value that's above our range that kind of offsets each other. It's the average that is what we're looking for. So we're 95% confident that this range captures the true mean of the canine life. If we go to this last one that we just did, interpretation, capital, all right, this one is, we are 99% confident that this range captures the true mean, oops, the true mean of Q2. Now, I don't know what the true mean is. I'd have to go back to my data generation files to figure out what the mean was of the distribution from which I pulled the random sample. So vast majority of the data that we work with, I've generated these. So I could go back and say, okay, well, this sample, like our RX, for example. RX, we knew we drew it from a population of 50. 50 is the true mean. All right, so this range that we just calculated, we are 95% confident that the true mean of 50, so the true mean, which is 50, is captured by this range. And it did. All right, so if we took repeated samples, if we did this, and we did do this, we've got 10 of us in here right now. All right, 10 of us in here, plus we had 11, which is in our presentation. All right, 95% of us should have a range that captures 50. Did anyone's range not capture 50?
Got really close to not capturing 50.
Right? All right, so I'm gonna try this again. Yeah, I captured that time. So on average, if I were to repeat this 100 times, I should average about 5 of my random samples that will generate a confidence interval that does not include 50. That's the idea of a 95% confidence interval. And why we say it the way we do. There's an easier way to do this too. There we go. Ooh, that was close, 50.3. 50.3. I bet we could change. Oh, there's one. Look at that. Random sample. Doesn't include 50. There's one. And you can just repeat that over and over and over again. So yeah, on average, 5% of our random samples will have a confidence interval that does not capture that true. That's what it means for 95%. If we do 99%, all right, we're looking at 99% confidence interval, then yeah, our 99% will likely be wider because we want to ensure that out of 100 samples, we only average one sample that gives us a confidence interval that does not include 50. All right. All right. I think we're going to stop here. Doing these confidence intervals, we'll do it in R, the interpretation and everything. We will not do this by hand on the closed book portion. That'll only be on the R stuff. All right. So make sure you review your probabilities. We had those extra probability problems the extra practice. I think I have the key for that. So if you wanted more, you can kind of do these. I'll also post the key to that once I get back to my office. All right. So our closed book portion is a little bit longer than it was on exam 1, just because we have more things to do. The terminology, they're about the same length in the number of terms that we need to know, but we've added like calculating probability, distinguishing between binomial Poisson distributions, interpreting normality and stuff. All right. All right. We'll call it quits there, and then we'll talk about confidence intervals. How do we increase it later on? Next week Wednesday we'll kind of continue with our confidence interval, and we'll talk about bootstrapping, and then start the first of our tests. All right. Have a good weekend.